The first, Gauss's law for electrostatics. It says that total electric flux passing through a closed surface is 1 over epsilon naught times the net charge enclosed in the surface. Mathematically, we can write phi of E is equal Q over epsilon naught. Phi of E is the symbol of electric flux. Electric flux is the total number of electric field lines passing through a surface area. It depends on the strength of the electric field lines and the surface area, and also the angle between the electric field lines and normal to the surface. So it is measured by the product of area and the components of the electric field intensity normal to the area. So we can write phi of E as closed integral E dot dA is equal Q over epsilon naught. This is the integral form of Gauss's law. But we can easily convert it into a differential form by applying the divergence theorem. And here is the differential form. Divergence of E is equal rho over epsilon naught. Now the question is how to apply Gauss's law. For that, the first thing, you should use the symmetry. That could be either spherical, cylindrical, or planar. And the second, you need to properly choose a Gaussian surface. For that, electric field should be parallel to surface area or perpendicular to surface area. The Gaussian surface is an imaginary surface that is closed from all sides, and the surface is symmetrical about charges. And the third, electric field should be symmetric on the surface. Now the question is, how much is the flux for a spherical Gaussian surface around a point charge? To answer this question, let's consider a spherical Gaussian surface having a point charge Q placed at its center, and at every point of the sphere, the electric field is radially outward and hence making angle 0 degree with area vector. So for finding the total flux now, using the formula phi of E is equal to closed integral E dot dA, and for the point charge, replace the electric field by 1 over 4 pi epsilon naught Q over R square. And because we have a sphere around the point charge, so replace dA with 4 pi R square, which is the area of the sphere. Hence we can get phi of E is equal to Q over epsilon naught. Dear students, that's all for today. In the next video, I'll discuss how to calculate electric field due to different charge distributions by applying the Gauss's law. Thanks for watching. If you like this video, make sure to subscribe for more. Hello everyone and welcome to my channel. This is the second video on the applications of Gauss's law. In this video, we will calculate the electric field due to the infinitely large uniformly charged plane sheet having surface charge density sigma. The electric field is everywhere normal to the plane, and the fields must be same in magnitude on each side of the plane sheet. Suppose there is a point P at a normal distance r from the plane sheet where we wish to find the electric field. We consider a Gaussian cylindrical surface here, which has axis normal to the sheet of charge, and the point P lies at its plane surface having radius a. Please note that the electric field is normal to the plane surface and parallel to the curved surface. Now, total flux through this Gaussian surface is electric field times the area of the curved surface plus electric field times the area of both planar surfaces. There is no contribution from the curved surface, as electric field is perpendicular to the surface area and cos of 90 degree is 0. So this term becomes 0 and we have only contribution from these two terms, and that is 2e pi a square, where pi a square is the area of the plane surface. We also know that the charge enclosed inside Gaussian surface is Q is equal sigma A, and by Gauss's law, we know that closed integral E dot ds is equal Q over epsilon naught. Now by equating the Gauss's law equation with the derived equation, we can get electric field is equal sigma over 2 epsilon naught. This equation tells us that electric field doesn't depend on the distance from the sheet, or we can say that the electric field of the infinite plane sheet does not fall off at all. It means that you can't escape from the infinite plane sheet. That's all for the today lecture. Thank you very much for watching. I would say please like and subscribe my channel. Hello everyone and welcome to my channel. In the previous video, we have discussed the Gauss's law for electrostatics, and I have added the link of that lecture in the description below. You can watch that video to refresh your concepts on Gauss's law. In this video, we will start discussion on the applications of Gauss's law. In this regard, we first select the case of long uniformly charged conductor with linear charge density lambda. As you can see here, positive charges are uniformly distributed on a long conductor where the electric field is directed radially outward from the conductor. Let P is a point at normal distance r from the conductor where we wish to find the electric field. Hence, to find the electric field, our Gaussian surface would be in the form of cylinder, where we have two types of surfaces. One is curved surface, where the angle between electric field and surface area is 0, and the electric field is tangential at the other two planar surfaces. One planar surface is this, and another planar surface at the bottom of the cylinder. Now, the total flux through this conductor will consist of two parts. First, a flux from a curved surface, and the second, a flux from two planar surfaces. As the angle between the electric field and the surface area at the curved surface is 0 degree, so we can write E ds cos of 0. And the angle between the electric field and the surface area for both planar surfaces is 90 degree. So simply we can write E ds cos of 90 degree, because cos of 90 degree is 0. So this whole term will become 0. So as a result, you can see we have our only contribution from the curved surface to the flux, and that is E 2 pi RL, where 2 pi RL is the area of curved cylinder surface. Because the total charge enclosed by the Gaussian surface is Q is equal to lambda L. Now, by taking the Gauss's law, closed integral E dot ds is equal to Q over epsilon naught, and by equating this equation with this equation, we can derive that E is equal to lambda over 2 epsilon naught R, where the electric field is inversely proportional to the distance r. In other words, this means that electric field falls off like 1 over r in the infinite long line case. This is all for today. In the next video, we will discuss how to calculate the field from a uniform plane sheet of charge. Thank you for your attention. Please like and subscribe my channel. Hello everyone. In the previous lecture, we calculated the electric field for the infinite plane sheet of charge, and that is E is equal to sigma over 2 epsilon naught, where electric field is independent of the distance. Now suppose we bring two infinite sheets close to one another, where one sheet is positively charged and the other is negatively charged, but both are charged with the same density. Now, what would be the electric field in the region between two sheets? and what would be the electric field in the region outside the sheets? To answer these questions, let's have a look at the direction of electric fields at all three regions. For example, the left sheet, being positively charged, produces a field sigma over 2 epsilon naught, which points away from it in the left to the left in the region 1 and to the right in region 2 and 3. The right sheet, being negatively charged, produces a field sigma over 2 epsilon naught, which points to the right in region 1 and 2 and to the left in region 3. Now, by adding the electric fields in each region, for example, the electric field between the two sheets, where the electric fields from left sheet and electric field from the right sheets are both in the same direction and also both have the same magnitude, sigma over 2 epsilon naught. Hence, by adding up both, we get sigma over epsilon naught, that is the electric field between the two sheets, which is uniform everywhere between the sheets. And in region 1 and region 3, where the electric fields from both sheets are in opposite direction to each other, so they cancel each other, and simply we get a zero electric field. So there is no electric field outside of sheets. Thank you very much. Hello everyone. In the previous lecture, we calculated the electric field between two infinitely large charged sheets and also the electric field in the region outside of the sheets, where one charged sheet was positively charged and the second one was negatively charged. Now in this lecture, we want to bring two infinitely long charge sheets again, but this time both are positively charged with the same charge densities. Now what would be the electric field in between the charge sheets and what would be the electric field outside of sheets? To answer these questions, let's have a look at the directions of electric fields at all three regions. Now, the left sheet, being positively charged, produces electric field which points away from it to the left in region 1 and to the right in region 2 and 3. The right sheet, which is being positively charged, produces electric field which points away from it to the right in region 3 and to the left in region 1 and 2. Now, by adding the electric fields in each region, but let's first consider that electric field pointing along the x-axis is taken as positive. Hence, the electric field between two sheets, where electric field from left sheet points right and electric field from right sheet points left. Hence, by adding up both, we get zero electric field. So this means electric field is zero everywhere between sheets. For the electric field in region 3, where electric field from both sheets point to the right, hence adding up both, we get sigma or epsilon naught. And the electric fields in region 1 also points in same direction, but in negative x direction. So when we add up both, we get minus sigma or epsilon naught. This means that there is no electric field between the sheets, but there exists electric field outside of the sheets. That's all for this topic. Thank you for your attention. Please like and subscribe my channel to get more videos. Thank you so much. Hello dear students. In this lecture, we consider a spherical shell of radius r having surface charge density sigma. We want to find the electric field inside, outside, and at the surface of the shell. Here we assume that the electric field is everywhere radial and is spherically symmetric. In the first case, we wish to find the electric field outside the shell at point P. For this, we consider a Gaussian surface of radius r, which is greater than radius of the shell. We have chosen a surface area ds at point P, and the electric field is normal to that surface area, and the angle between the surface area and the electric field is 0. Now, total flux through the Gaussian surface is equal to closed integral E dot ds, which is equal E ds cos of 0. Cos of 0 tends to 1. So this becomes E times closed integral ds. The Gaussian surface area is 4 pi r square. So we can write E electric field times 4 pi r square. The total charge enclosed by the Gaussian surface is Q. And by applying the Gauss's law, closed integral E dot ds is equal to Q over epsilon naught. And by equating the Gaussian law equation with the derived equation, we get electric field is equal to Q over 4 pi epsilon naught r square. This shows that the electric field outside of the shell is like the electric field of a point charge. Now, in the second case, to find the electric field at the surface of the shell, for that, when we decrease the radius of the outside Gaussian surface up to the surface of the shell, we find that electric field increases. And that we can see in the graph here, where the variation of the electric field with respect to the distance from the center, or in the first case, up to the distance of the surface, look like this, where you can see the electric field is maximum at this point, and that point is exactly the point at the surface. And whenever you go away from the surface, you can see the electric field decreases. Now, in the third case, to find the electric field inside the shell, we draw a Gaussian surface of radius r, where we pointed a point P, where we want to find the electric field, but there is no charge inside the Gaussian surface. So this means if there is no charge, there is no electric field. So by Gauss's law, closed integral E dot ds is equal to Q over epsilon naught. Q is 0, so electric field is 0. So this means inside the electric field is 0, which you can see in the graph here. From the center up to the surface, you see electric field will 0. Once you reach to the surface, the electric field will maximum. And when you move away from the surface, you can see electric field will decrease again. So dear students, this is all about the lecture. And thank you so much for watching. Please subscribe my channel and share with your friends. Thank you so much. Hello dear students. In the last lecture, we have taken a case of spherical shell, and we found the electric field inside, outside, and at the surface of the shell. Now in this lecture, we consider a solid sphere of radius r having a volumetric charge density rho, and we want to find the electric field inside, outside, and at the surface of the solid sphere. And we assume that the electric field is everywhere radial and is spherically symmetric. Now in the first case, we want to find the electric field outside of the sphere. For this, we consider a Gaussian surface of radius r, which is greater than the radius of a sphere. And we take a point P, where we choose a surface area ds at point P, on which the electric field is normal to the surface area, and the angle between the electric field and the surface area is 0. Now the total flux through the Gaussian surface is equal to closed integral E dot ds, that equal to closed integral E ds cos of 0. Because the electric angle between the electric field and ds is 0, so we have cos of 0 here, which goes to 1, and we get electric field and times closed integral ds. And the surface and the area of the Gaussian surface 4 pi r square. So we replace closed integral ds by 4 pi r square. The charge enclosed by the Gaussian surface is Q. And now by applying the Gauss's law, closed integral E dot ds is equal to Q over epsilon naught. And by equating the Gauss's law with this derived equation, we get electric field is equal to Q over 4 pi epsilon naught r square. Uh, Here we can see that the field outside of the sphere is like that of a point charge. And the second result is that this is also same field like in the case of charged shell when we found the electric field outside of the shell. Now, in the second case, we want to find the electric field on the surface of the sphere. So for that, if we decrease the if we decrease the radius of a Gaussian surface up to the Gaussian sphere up to the surface of the sphere, then we get electric field is equal to Q over 4 pi epsilon naught capital R square. And capital R is the radius of sphere. Now, how both results look like if we plot them in the form of graph, where the electric field versus the distance from the center of the sphere. You can see here when you are at the exactly at the surface of the sphere, you have a maximum electric field, and when you move away from the surface of the sphere, electric field decreases. This is what we have the result for the case of outside of the sphere. Now, in the case of inside of the sphere, let's take a Gaussian surface of radius r now inside of the sphere, and we take a point P where we choose a surface area ds, on which the electric field is radial and symmetric all over the Gaussian surface. And now the total charge inside the Gaussian surface, that would be Q is equal to rho v, where rho is the charge per unit volume, and this volume is the volume of a Gaussian surface, and that is 4 over 3 pi r cube. Now by applying the Gauss's law, which is closed integral E dot ds is equal to Q or epsilon naught, and now by putting the values of ds, area of the Gaussian surface, and Q, the total charge inside the Gaussian surface. So we have electric field times 4 pi r square is equal rho into 4 over 3 pi r cube. So we get electric field is equal rho r over 3 epsilon naught. It shows that the electric field inside of the sphere is proportional to the distance from center. So if we see this in a plot, we have a straight line exactly at the center of the sphere. You have a zero electric field. Once you move away from the center up to the surface, it increases. It increases, and once you reach at the surface, the electric field is maximum. And when you move away from the surface, electric field decreases. Okay, dears, this is all about today's lecture. If you like the video. Hello, dear students. In the last two lectures, we have discussed in detail the electric field inside, outside, and at the surface of the spherical shell and solid sphere. The links of both lectures are given in the description below. You may watch again. In this lecture, we want to do a brief comparison between both cases. A spherical shell surrounding an empty sphere has the entire charge on its surface along with uniform surface charge density sigma. There is a uniformly charged solid sphere of radius r having total charge q enclosed along with uniform volume charge density rho. Assume that the electric field is radial and equal in magnitude at all points at the same distance from the center. In the first case, while finding the electric field outside of the solid sphere and shell, we find that the electric fields of both are just like that for a point charge. While in the case when we decrease the radius of the outside Gaussian surface up to the surface of the solid sphere or shell, we found that electric field is proportional to 1 over r square. Hence, at this point, we conclude that electric field outside of the solid is same as in the case of charged spherical shell, and the electric field on the surface of a sphere is same as in the case of a shell. Now, to find the electric field inside the sphere, we draw a Gaussian sphere of radius r less than the radius of the sphere. The charge inside our Gaussian surface is Q is equal to rho v. Q is equal to rho v, where v is the volume of the Gaussian sphere. And now by using the Gauss's law, we find that the magnitude of the electric field is proportional to the radius and is directed radially outward. Now, in the case of shell, a Gaussian inside the shell contains no charge because all charges are on the surface of the shell. Hence, we get immediately from Gauss's law that electric field everywhere inside the shell is zero. So now in the graph, we can understand easily the cases of the electric field variation with respect to radius or distance from the radius. In spherical case, the electric field inside the sphere of uniform charge is zero at the center and increases linearly with respect to radius r. We have maximum electric field at the surface and decreases while moving away from the surface sphere surface. Now let's look at the graph for a shell case where the electric field on the surface of shell is same as in the case of the solid sphere, and the electric field is decreasing in the same way as was the case of a sphere. Only inside there are difference. Inside shell there is no charge, so no electric field, and inside the sphere, first electric field is zero at the center, but after that it increases linearly with respect to radius and then decreases while moving away from the surface of the sphere. Okay, dear students, that's all for this lecture. Please subscribe my channel and share with your friends. Thanks.